All right. Hi, everyone. I thought I'd just run through our latest quiz here, give you a little something to compare and contrast with, see how I'd like you to do things, see things that maybe you could do better. Just kind of polishing up before the exam here, and we're going to cover the most recent couple sections right before the exam. And additionally, I was asked about some conditional and absolute convergence questions. So go ahead and run through one of those. So let's run through an example here. Test series for convergence. Sum n equals 1 to infinity, n plus 1 over n cubed plus n. Yeah, plus n. Okay. So there's a few ways we can go about this one, but the easiest thing to do generally with rational functions like this is some sort of comparison test. In general, from just experience, honestly, we want to compare leading coefficient or leading terms of each of these polynomials in the numerator and denominator. So we want to compare with something of the form n over n cubed, which is 1 over n squared, okay? So I'm going to say we know that the sum n equals 1 to infinity of 1 over n squared is convergent by p-test, right? I would also accept just leaving this alone and saying it's convergent because 1 over n and 1 over n squared are very well known for being divergent and convergent respectively. So we know that this is convergent by p-test. So examine limit as n approaches infinity of 1 over, excuse me, I want to put the other summand on top here, n plus 1 over n cubed plus n over 1 over n squared, which is equal to the limit as n approaches infinity of n squared times n plus 1 over n cubed plus n. And we can go ahead and distribute in the numerator and get n cubed plus n squared over n cubed plus n. And limit as n approaches infinity. So we can divide everything by n cubed. So that will look like 1 plus n squared over n cubed is 1 over n. And then this is 1 plus n over n cubed is 1 over n squared. Okay. And then we can go ahead and evaluate the limit. This term goes to 0. This term goes to 0. This is just 1. 1 is greater than 0. And we can say, therefore, by limit comparison, test, both series, well, we know that from the limit comparison test, if this is greater than 0, like it is, then both series either converge or diverge. And since we acknowledge that 1 over n squared is convergent, we can conclude that by the limit comparison test, the series n equals 1 to infinity, n plus 1 over n cubed plus n is convergent. Okay. All right. Let's run through another one. Test the series for convergence. So we take the sum k equals 1 to infinity of ln of k over k, should just be over k. Let me make sure that that's right. In my notes here, I have k squared, but I'm pretty sure it should just be 1 over k. Okay, that's 1 over k. So we'll say apply direct comparison with the harmonic series, 1 over n. Okay? Now we need to be just a little careful here, okay? Because we need to verify in full generality that this summand is less than this summand, or less than or equal to, okay? So we note that 1 over n is less than or equal to, well, excuse me, I should be using k's here, 1 over k. So 1 over k is less than log of k over k when k is greater than or equal to 3. Okay? And this follows from the property of the graph of the log. It does something like this, where this is 1, 0. I'll write that a little bigger. The intercept is 1, 0. And at e, which is 2.71, the y value is 1. So at any point past 2.71, log of k is bigger than 1. But since we're interested in positive integer valued functions here, we're just gonna round up to the nearest integer and say when k is greater than or equal to 3. Okay? So this inequality is pretty obvious. We don't need to do any more work than that, because we have the same denominator and a larger numerator, and larger in magnitude numerator. So that kind of inequality that's fine. There are situations when we would need to show just a little more work and show that the inequality holds true. But yeah, we can go ahead and say this one is pretty obvious. Okay, so we have our inequality proved here, and now we need to say, okay, well, it is well known, and we can prove this by p-test again, but it's well known that the sum k equals 1 to infinity of 1 over k is divergent. It's kind of the prototypical example of a divergent series, which tells us, therefore, the sum, and just to be overly pedantic, I'm actually going to change the index here to 3. While it is true for k equals 1, since we're doing comparison, let's just line the indices up so we don't have anything else to worry about. So the sum k equals 3 to infinity of log k over k is divergent by direct comparison with the harmonic series. Okay, now we need to be a little careful here because we changed the index, right? This is going from 3 to infinity, but the one we started with goes from 1 to infinity. So how do we reconcile that? Well, a series diverges or converges based on the infinite part of the series. It's the infinite tail. We can pull off as many, we can index from any finite number here in the bottom, and that's not going to matter because we'll still be adding finitely many finite things and then the series. So finitely many finite things will be a finite value. Might be huge, but it will be finite. It's the series that may or may not converge. Okay, so because this converges, because this converges, sorry, diverges, excuse me, because this diverges, by adding even negative things, it's not going to affect the convergence or divergence. So from this, we can conclude that therefore the full series k equals 1 to infinity of log of k over k diverges. Okay, adding or subtracting finitely many finite things from a divergent series is not going to change the fact that it diverges. So it's a very weird thing to be thinking about, but it's the convergence or divergence is dictated by that infinite tail of the series. Okay, so any combination of adding or subtracting finite numbers is not going to affect that. Okay, so this is being a little, it's being very precise. We're saying that, okay, we can draw the conclusion that this series diverges, but the full series will also diverge. Okay, so we have to be careful about our indices in adjusting those accordingly, because sometimes we will need to adjust them, draw our conclusion about convergence or divergence, and then come back to the full series. Okay, so let's run through another example. And I definitely want you to say, okay, we draw our conclusion. So here's why this series can fit the bill. Here's my inequality. Here's my limit, whatever. Justify why you can use a test, and then say that, okay, we draw our conclusion by saying this series fits the bill for this test, and it fits the bill for this test, and the test says that it either diverges or converges, and it's this test. Okay? All right, so test the series for convergence. The sum n equals 1 to infinity, -1 to the n plus 1, n squared over n cubed plus 4. Okay, so this is our alternating series. So there's a decent possibility that we want to use alternating series test. Not all series that alternate in sign will fall into the category of alternating series test, but it's generally a good place to start. Okay, so we need to show that it fits the bill for this alternating series test. So we need to demonstrate that this limit is 0. Okay, so consider limit as n approaches infinity of n squared over n cubed plus 4. And that's equal to limit n goes to infinity. Now we can go ahead and divide everything. You can think about it 2 ways. I'll do it like this. Let's multiply by 1 over n cubed over 1 over n cubed. It's a fancy 1. We're not changing the value of what we're taking the limit of. We're just multiplying by 1, so it doesn't change the value. You can think about this as dividing the numerator and denominator by n cubed, however you want to think about it. But this boils down to 1 over n over 1 plus 4 over n cubed, and 1 over n goes to 0, and 4 over n cubed goes to 0. So we have something of the form 0 over 1, which is 0. Okay, so that's half of the alternating series test. The other half is we need to show that n squared over n cubed plus 4 is decreasing. Okay, and even if you get stuck in the algebra or the calculus trying to show that, even writing down, okay, here's what I want to do. I am trying to justify the application of a convergence test, and I'm aware of the conditions. Like, that can get you a lot of partial credit. You know, if you get stuck in the weeds, you know, with algebra, that's fine. I want to know from a conceptual standpoint that you knew what you were doing, and indicating to me that I'm checking the conditions and making sure that we can apply this test is huge. It's going to give you a lot of partial credit. Okay, so we need to show that this is decreasing. Well, the easiest way to do that is with calculus. Okay, so we consider f of x is x squared over x cubed plus 4. Okay, and the reason I switched to x's is because a function that is integer valued can't be differentiated, right? So we have to switch to something that can be differentiated, and we say that x is a real number, right? And we can even be more specific than that and say that, well, x has to be contained within the interval 1 to infinity to match our sum 1 to infinity. Okay? All right, so let's rewrite f of x in a little more calculus-friendly form here, and then differentiate. So f prime of x is 2x times x cubed plus 4 to the negative 1 plus x squared, bring the power down, x cubed plus 4, reduce the power by 1, and then multiply by the derivative of this because of chain rule. So that should be 3x squared. So I have that f prime of x is 2x over x cubed plus 4. So I have this in the numerator, so that's minus 3x to the 4th over x cubed plus 4, quantity squared. And now I'm going to get a common denominator, so I'm going to multiply this term, top and bottom, by x cubed plus 4. So we have 2 times x cubed plus 4 minus 3x to the 4th over x cubed plus 4 quantity squared. And then we can go ahead and distribute and have 2x cubed I made an algebra mistake here. I should have an x here and here. Okay, so that would be 2x to the 4th plus 8x minus 3x to the 4th over x cubed plus 4 quantity squared. Okay, so here's a good time for you to, just write in English what you're doing and explain, because not everything in math can be done mathematically, particularly when we've asked for a level of rigor that we're asking for. Okay, so we'll note that the denominator, x cubed plus 4 quantity squared, is positive for all x values in the interval 1 to infinity. Okay, so the only way that f prime will be negative is if the numerator is negative. Okay, so I'm going to make some space up here. So we need to see where the numerator is going to be negative. So simplifying, I can subtract 2x to the fourth minus 3x to the fourth and get 8x minus x to the fourth is less than 0. We want to know what x values make this inequality true. So we can go ahead and factor out an x. So that's 8 minus x cubed is less than 0. Okay? But we're only interested in values of x that lie in this window, 1 to infinity. So we're assuming that x is positive and non-zero, so we can go ahead and divide both sides by that. Okay? We can divide by x, divide by x. We're not going to flip the inequality because it's positive, and we're not going to divide by 0. So we're only concerned with 8 minus x cubed. I don't need that parentheses anymore. We're only concerned with 8 minus x cubed being less than 0, which tells us that 8 is less than x cubed. Just 1 second. I may have missed a sign here. No, okay. We're good. Okay. So this tells us that x has to be strictly greater than 2. Okay, those are the x values that are going to satisfy the inequality we wanted to make the first derivative negative. Okay, if the first derivative is negative, then we have that as decreasing, right? So I'm going to erase some here. So now we can go back and we can say, all right, well, we're going to restrict the domain just a little bit more. We're going to only consider values from 3 to infinity. Okay, then we can guarantee that is decreasing. All right, so f of x is x squared over x cubed plus 4 is decreasing on the interval 3 to infinity. Okay, so we can go ahead and apply the alternating series test. We're going to modify this a little bit. We're going to say, okay, the sum n equals 1 to infinity of minus 1 to the n plus 1 n squared over n cubed plus 4. Sorry, n equals 3 to infinity. Okay, that looks better. Is convergent by alternating series test. Okay, and it's because the limit is 0 and it's decreasing on the interval 3 to infinity. So that's why these indices work this way. Okay, so the infinite part of it is convergent. So adding back the first 2 terms that we're missing is not going to affect the convergence at all. It's still going to be convergent. We're just adding and subtracting a finite number of finite things. Okay, so therefore the full series n equals 1 to infinity minus 1 to the n plus 1 over, sorry, excuse me, times n squared n cubed plus 4 is convergent. Okay, these are tricky things. This is not an easy section. They're definitely a new way of thinking about math, but they're extraordinarily useful. This is, believe it or not, the foundation for how calculators work. Your calculator doesn't know what cosine is, but we can approximate it well enough. we can approximate it using operations that your calculator knows how to do, I should say. Okay, last one, or second to last one, sorry. Test the series for convergence. And the series is sum n equals 1 to infinity, minus 1 to the n plus 1, n e to the minus n. Okay, again, we have an alternating series. Might want to see if it passes the alternating series test. Okay, so we need two pieces. I'll switch colors again here. We need piece 1, the limit as n approaches infinity. N e to the minus n has to be 0. And 2, we need the sequence a sub n equals n e to the minus n decreasing. Okay, so for the first part, we're going to just say limit as n approaches infinity of n over e to the n, which is of the form infinity over infinity. So make a little note, infinity over infinity. So by L'Hopital, we can differentiate the numerator and denominator. And I'm being a little sloppy with notation here. Technically, I should pass to a function of x, which will be differentiable, but I don't think I'm going to mark you off for something like that. Just go ahead and differentiate. So that gives us 1 over e to the n, which is 0. So check. 0. Okay, so that part is satisfied. And now we need to check for decreasing. So again, we're going to use our calculus. So let f of x equal x e to the minus x. We wish to show f of x is decreasing. Okay, and this is what I'm talking about. Even if you get stuck in the weeds, just even writing it out and saying, okay, here's what I know I need to do. That can go a long way in terms of partial credit. So if f of x is x e to the minus x, then f prime of x is e to the minus x, and we pick up a negative sign, minus x e to the minus x, right? Just from product and chain rule. So then we can set f prime of x to be less than 0, and we want to find the x values that make that true. Okay. So let's say e to the minus x e to the minus x is less than 0. We can factor out an e to the minus x. And now we can divide. But you have to justify why you can divide. E to the minus x is going to be positive. It's just a reflection around the y-axis, right, of our regular e to the x function, which we know is positive. Well, it's not 0 and it's positive, so that's even better. So our division is defined and it doesn't change the inequality sign. So we can go ahead and divide that out, and we're left with 1 minus x is less than 0, which tells us that x has to be strictly greater than 1. Okay, so we'll go ahead and we'll take x values in the interval 2 to infinity. Okay. Okay. So now we're ready to apply alternating series test. So the sum n equals 2 to infinity, right? Because we changed the interval just a little bit, of minus 1 to the n plus 1, n e to the minus n is convergent by alternating series test. Therefore, the full sum, That's a horrible signal, sorry. Therefore, the full sum, n equals 1 to infinity, minus 1 to the n plus 1, n e to the minus n, is convergent. Because we're only adding the one extra term. Okay? All right, we'll do the last one here. Determine if the series is absolutely or conditionally convergent. Okay? So the given series is sum n equals 1 to infinity minus 1 to the n minus 1 over square root of n. Okay? I'm going to put a star here just for easy referencing. Okay, so first we check if the series is absolutely convergent. Okay, and we test absolutely convergent first, because if we're absolutely convergent, that is a stronger quality than being conditionally convergent. Okay, and the intuition behind that is, you know, if I'm adding a bunch of positive things and they come up to a finite value, then definitely if I'm add, then subtract, then add, then subtract, and add, then subtract, should give me a smaller thing. Now, that's not very technical, but that's kind of how I remembered it when I was taking this class. So absolute convergence implies conditional convergence. If you have absolute convergence, you are definitely conditionally convergent. Okay, it's just a stronger condition here. So we need to see if the absolute value of our sum n is a convergent series. Okay, so go ahead and check that out. So absolute value minus 1 to the n minus 1 over square root of n. And it's worth noting that absolute value of x can be defined as the square root of x squared. Okay, so if you're savvy with your exponent properties, you'll know that we can split absolute values over products and quotients like this. So this is minus 1 to the n minus 1 over absolute value of the square root of n. But the square root of n, if you recall the graph of the square root, is always positive. So that doesn't change the denominator at all. And the numerator is either 1 or minus 1. So the absolute value of that is just going to be 1. So we're looking at the series n equals 1 to infinity of 1 over square root of n. Okay. Well, this one's pretty easy to see that by p-test, with p is 1/2, the sum 1 over square root of n diverges. Okay, so therefore, star, the original series that we started with, is not absolutely convergent. Okay. All right, so now we need to test for conditional convergence. So I'll go ahead and make some room here. Okay. And this is an alternating series, so I think that's a good place to start. Apply alternating series test. Okay, so it's going to be the same kind of deal. We need to verify two things. We need the limit as n approaches infinity, 1 over the square root of n to be 0, and it is. So easy check mark there. And we need the 1 over square root of n decreasing. Okay. And again, we can pass to a function of x and say this is square root of x, 1 over the square root of x, which is x to the negative 1/2, okay, which tells us that f prime of x is minus 1 over 2 root x. Is that right? No, sorry. Minus 1 over 2x to the, and then we subtract 1, and that should be minus 3/2, excuse me. F prime of x is minus 1 over, and I'm honestly just going to leave it as 3/2. I think that's it's going to be, it's not necessary to convert back to the radical form because the next step is just going to clear this up. But so for all x values in the interval 1 to infinity, if we take the square root of 1 or the square root of whatever, that's going to be positive. And then if we cube it, that's also going to be positive. So we conclude that the denominator is always going to be positive. And with this negative sign here, we have that f prime of x is less than 0. Okay? So for all x values in that interval, f prime of x is less than 0. Okay. So that tells us that we can apply alternating series test. And make our final conclusion, which is that the series n equals 1 to infinity minus 1 to the n minus 1 over square root of n converges by alternating series test. Okay. Which tells us that the series is conditionally convergent. Okay, it's a pretty subtle distinction, but it's one that's very good to know. So that's all I had for you today. That's all I think I wanted to cover. So, you know, if there's any last minute questions you have, anything you want to ask me, let me know. Other than that, good luck on your celebration of knowledge.